Well, regarding simulation, I wanted just to let you know also that dealing with hydraulic. So this is a particular case when you have closed somewhere. Or for example, when you have cooling water distribution system that is a closed loop. Okay, because the normally the cooling water circuit start with you have a well or a tank of water, and you have your pump, that is your source of pressure, and then you have the distribution. You go to heat exchanger, condenser, cooler, etc. And then at the end, they join together in the return header that go into a cooling tower. Okay, and then from the cooling tower, this water goes into a tank and then to the pump again. Okay, and this is like a closed loop. And then this kind of simulation, so it's very interesting because you can, let's say, see the distribution of the water to any process plant depending on the equivalent length of that plant and the equivalent diameter, because you have to specify one equivalent diameter for any process plant. And then, well, this is when you want to evaluate the circuit, the loop, and the distribution, the water distribution pumps. But then after that, you go inside any plant, and then you make the study of the distribution for your water between the inlet and the outlet, because you already have the pressure drop. You know, when you run the big simulation, so you have the inlet pressure and the outlet pressure for that process plant. And then you start to check with that differential pressure, how is the water distribution for any piece of heat exchanger that you have inside your process plant. And don't forget to include the elevation of the heat exchanger, because this is something that happened to me in a project that they have inlet header pressure, outlet header pressure, and the distribution inside the heat exchanger. And according to the simulation they run, they size the main distribution header inside the process plant. Okay. However, they didn't take into account the elevation of the heat exchangers. So they run the simulation as it was a flat simulation, and they go say perfect. But when you see the plan like this, so you see a photograph. But when you see the plan like this, you start to see the elevation of the equipment. The guy say, what happened? The condensers are there.
There will be a head that should be.
Yes, and then this static head.
Yes, static head.
For that simulation they run has eaten all the pressure. Okay, and then for us to solve the problem, this main header need to be increased in size, because we need to decrease the pressure drop in there to have enough pressure in here for that, let's say, negative static head that was influencing the flow rate. And then what happened? What happened in the reality if you don't do that? So that the water will, let's say, will move up to here, and then the rest of the flow of the water is flowing that way. Okay, and then you can see that the water will never reach the that elevation.
Yeah.
And then your condenser that is in here is wet, sorry, is dry, don't have any water off, or the expected flow of water is lower than the one required to condensation. And then operationally, you start to have problems. And then this is part of the thing when you are working in operations. There are a lot of things as a process engineer that you have to identify. Okay, to identify things like this. So where can be the bottleneck? Why one cooler is cooling or not? Okay, I remember several cases for cooling water. I don't remember if we discussed this topic with you. I think I did.
Not yet.
I think that it was a case that they have a couple of very big condensers, and the condenser were running in parallel. They have 2 shells and 2 shells. Okay, there were 4 in parallel, and then let me try to draw it. It's better like this. Try to. This is one of the cases I would like to discuss in a webinar.
It will be interesting.
This is operational things that happen, and then you have to look for a solution. They have something. The header was like this. Let me see if you can see it.
Yeah, I can see. Yeah.
Okay, so the water was entering like this, and then you have four condensers running parallel 2 and 2, and then they have butterfly bars at the outlet. And then what happened in that circuit? That the flow of water, so we're running that way, and then the most of the flow were going like this. And nothing, or very few flow rate of water was coming that way. Okay, because there I told them, so it is not a matter of a capacity of the pipeline. It's a matter of, let's say, piping arrangement. Because nothing is stopping this flow to go that way. And then I told him, you remember one of the laws of Newton, I don't remember if it's number 1 or number 2, that if you are moving forward, somebody try to stop you, you try to continue moving forward.
Yeah.
And it's something similar that is happening there. There is nothing stopping that water to go that way. And then what they did operationally, if they closed that valve to try to pull more water to this tube. I say, perfect, but this is not a good solution. We need to do something with that pipe arrangement. The first thing that you have to do is to try to stop that flow rate. Okay? And then to change. You remember that case that I have for the 2 flare that I presented in it's similar to this. So it's a matter of piping arrangement to solve the problem. It was not a problem of piping size. It was not a problem of you managed to close or to open a manual valve. And then when we try to run this case in a simulation, so the simulation says this. Simulation say more than 70% of the flow rate is going to the far end because nobody is stopping that flow to go that way. Then you have to do something. We need to introduce a piping arrangement, and it was costly because we were talking about 20 inches pipelines. So it was very big pipelines. And then this is the recommendation I did for them to solve that problem. They said, no, the problem is not the pipeline side. The problem are not the condenser. The problem is the piping arrangement that need to be upgraded. And then when you run this simulation, so the simulation can give you some ideas or can give you some problems. And then I remember that one of these nodes, I think what this node, it was not balanced. So then it was giving negative pressure as if the flow rate was going that way or that way. Okay, and then we say, okay, it is there that you have a problem of distribution, so we have to do something. Okay, so the simulation is giving you some ideas or some things that, and then the flow rate as well. It was saying, okay, perfect. I got the convergence. But when we check the flow rate, so let's say 80% from here, 20% from there. So you was expecting 50-50. Okay, and then it's things like that that are very interesting when running hydraulics simulation, and then when you have loops like this. In this case that you have right now with the production wells, the potential problem is when you introduce a new well, a new production well into that existing network, because when you run the network for the first time, you already have the size of the main headers, the pipeline header. But if you have not considering that this to size that pipeline for capacities, you will have troubles. Okay? And then this is one issue that may happen to you when you pull some new production wells into your network. And also consider something that when you introduce, well, in this case, in the case of the production well, it's not like that, because you have several well production in that side, and then you have the processing plant in that side. So it's not a network, a complicated network. But however, when you have loops like this for the cooling water system, when you introduce a new cooler, depending on in which location you introduce it, so you will see that it will unbalance another coolers, the flow of water to another coolers, and then the flow of water from your pump. Okay, they will try to pull some additional water from the pump, but it will take a flow from another heat exchanger that are already in network. And then this is something that you have to be aware when you start to work in a refinery or in a plant that where you have networks like this. Because the people used to say, so the operator and the people from the plant, they used to say that the pumps have enough capacity. They're perfect, the pump have enough capacity. Or depending on where you link your new service or your new plant, so the pumps will be affected and or another heat exchanger. And then you may take a little bit of water from the pump, but another flow from the other exchanger to go into the new service. And then that heat exchanger can be receiving less water than required to cool down or to condense the other service. Then you have to be aware of this. Because the people used to say, no problem. We have enough capacity. No, my friend, you have to run your simulation. And then you have to run your simulation, and then you have to look what is the best, let's say, recommendable location for the new service. Because depending on where you put or you introduce this new service, so you can balance or unbalance another services. Okay, and normally in this kind of circuits, the plants that has problems are the ones that are far from the source. Okay, so for example, you have your, I remember that in the refineries I have worked, the plant that is close to the cooling water pumps are the power generation plants. And then the power generation plant require a very huge flow of water. And then just at the fact that they are very close to the source, then they take practically all the water that are given by the pumps. And then the other plants far away so start to have problems because this, let's say, bad distribution.